Hello dear students, with this video we start with the properties of alcohols and we shall be talking about the right side of this flow chart that we had discussed earlier. So we are going to take each of these reactions in detail, but before we do that, please don't forget your pen and paper. So I hope you have a separate notebook ready where we can write the reactions we are going to study in today's lesson. I'm going to discuss the properties of oxidation and dehydration shown by alcohols. Based on our earlier learning where I had told you that alcohols are oxidized to aldehydes and aldehydes are oxidized to carboxylic acids, whereas on reduction, carboxylic acids give you aldehyde and aldehydes can be reduced to alcohols. This we had discussed under the preparatory methods for alcohols. Now, in order to understand the products of oxidation of alcohols, what I'm going to do is I'm going to take the functional group of a primary alcohol. Now in a primary alcohol you have CH2OH as your functional group, right? Now when oxidation happens, now we are not going to deal with the mechanism exactly, but to make things easy for you, what will happen is it is these CH bonds which get oxidized. So the CH bond over here will get converted into COH, right, in the presence of an oxidizing agent. Now we know that two OH groups attached to carbon, it's not a very stable arrangement. Why? Because the oxygen atoms over here have lone pair of electrons and both of them are like, take my electrons, so carbon will be a little confused. So that is why when we have two OH groups attached to the same carbon atom, to remove the burden on the carbon, one water molecule is removed. Now when this water molecule will be removed, see what is going to happen to the bond, CH, and this will convert to a double bond because the lone pair of electrons of oxygen will be shared by carbon. Look at the structure carefully. What functional group is this? Yes, absolutely. It's an aldehydic functional group, right? So that means your 1 degree alcohol has got converted into an aldehyde. But at the same time, notice that there is one more CH group which is present which can be oxidized further. But interestingly, now carbon is more alert. One of its CH bonds has already been oxidized. So if I try to oxidize this CH group, I will have to use a strong oxidizing agent in order to do that. So C double bond O, and what will happen? It will convert to OH. Now again look carefully, what is this functional group? Just put it together, COOH. Yes, absolutely right, we get a carboxylic acid here. In other words, when you oxidize a primary alcohol, it will get oxidized to an aldehyde first, and further on, if I have a strong oxidizing agent, this aldehyde gets converted into carboxylic acid. Let us look at the number of carbon atoms. So let us suppose I start with some alkyl group over here. So RCH2OH, this is my original alcohol. This has now got converted into RCHO. That's my aldehyde. Now RCHO means the number of carbon atoms. So here there were N plus 1 carbon atom. Some number of carbon atoms. So for example, this R could also be your CH3. So CH3, CH2OH. is getting converted into CH3CHO. The number of carbon atoms is remaining the same. Similarly, your final product over here, the carboxylic acid, would be CH3COOH, right? Or if you have taken just as a general alkyl group, it becomes RCOOH. In other words, if I start with n number of carbon atoms, the number of carbon atoms in the aldehyde remains the same. The total number, inclusive of the functional group carbon, the aldehydic carbon or the acidic carbon. So I've got n carbon atoms, and same way for the carboxylic acid, I get n carbon atoms. So oxidation of primary alcohols gives aldehydes containing the same number of carbon atoms, or carboxylic acids giving us the same number of carbon atoms. Okay, now let's have a look at a compound which is a secondary alcohol. So CH, there will be a carbon over here because there will be some other alkyl group attached, and OH. So look at the functional group that I've got. I've got a CHOH as the functional group. So how many CH bonds do you have over here? You have only one CH bond. So try oxidizing it. So C, this remains here. H converts to OH, and OH again, look at what you've got. You've got a scenario where there are two OH groups attached to the same carbon atom. So we need to offload it. And this becomes, yes, this is C, double bond O, single bond C. Of course, there will be a C over here, a carbon atom or some alkyl group. Now look carefully again, what functional group have you got? C. So let me arrange it like this. Probably it will remind you of some functional group, right? Two free valencies, two alkyl groups attached to C double bond O. Well done. This is a ketone, right? In other words, I started with a secondary alcohol. When we oxidized it, it got converted into a ketone. Now look at it carefully. Does it have any more CH bonding at the carbonyl carbon, at the carbon which is attached to double bond O? Look at it carefully. No, right? So if I try to oxidize it further using some very strong oxidizing agents, what do you think will happen? Yes, it will cause this bond, one of the bonds, to break because we are using very strong oxidizing agents. So with the result, you will have here a CH3, C, double bond O, OH. That means we are converting it into an acid, but look at the number of carbon atoms. You started with 1, 2, 3. So let me put a carbon here. Let me put a carbon here. You started with 1, 2 and 3 carbon atoms. You had a ketone with the same number of carbon atoms. But look at the acid. Yes, the number of carbon atoms has gone down. How many? Where does the cleavage happen? Where does the breakdown happen? Is further off. That study is required for you need to understand it by an in-depth study. We are not going to go into that much detail at present. So we say acid containing lesser number of carbon atoms, right? And of course we'll have carbon dioxide because RC here, the CH group over here, the alkyl group over here will get oxidized. So we may end up having carbon dioxide and water as some of the side products. So in 2-degree alcohols, first of all, on mild oxidation, they get converted into ketone containing same number of carbon atoms, whereas on strong oxidation, you get acids with lesser number of carbon atoms. And you would be able to see the effervescence of carbon dioxide as well. What are the oxidizing agents that we shall be dealing with in these oxidation reactions? Don't worry, we're going to talk about those in greater detail as well. So as you can see in the flowchart, which I hope you've kept on the side, what you can do is take the flowchart, keep it as a ready reference on the side, and keep writing the reactions looking at the flowchart. That's a very good and easy way to remember the topic. So look at the oxidizing agents. You've got acidified potassium dichromate, alkaline KMnO4, acidified KMnO4, and chromic acid. Greater detail a little later in the video. Let us now have a look at tertiary alcohols. So tertiary alcohols mean we've got the OH attached to a carbon which is attached to 3 other carbon atoms. Now look at that. Where can oxidation happen? Nowhere. So what will happen is, first of all, I will have to use very strong oxidizing agents in the first stage itself. And because I am using strong oxidizing agents, what will happen? It is called as oxidative cleavage. That means there will be a bond breaking taking place as well as oxidation. So what will happen here? The smaller alkyl group is released as carbon dioxide and water, whereas the bigger group over here attached to OH will get converted into a ketone, CH3C, CH3 double bond O, because our COH over here will get converted into ketone. How? Can you think of, can you connect to your learning in the previous slide? Try it. So what has happened over here? Oxidation has taken place, but by breaking off the bond, and that too under drastic conditions. So what can we write about 3-degree alcohols? That 3-degree alcohols on strong oxidation give us ketones containing lesser number, right? Less than the number of carbon atoms has gone down. 1, 2, 3, 4, whereas here it's 1, 2, 3. So ketones containing lesser number of carbon atoms are formed and further oxidation does not take place. So I've listed all these 3 behaviors in the form of 3 bullet points, which will help us to remember the properties at a glance, the properties of getting oxidized. Okay, so inquisitive to know what are the oxidizing agents that we can use. Acidified potassium dichromate, acidified potassium permanganate, alkaline KMnO4, Jones reagent, Collins reagent. Oh, too many to learn, right? Now, acidified potassium dichromate, acidified KMnO4 and alkaline KMnO4 have also been discussed separately under the topic of D and F block elements on the channel, where we have discussed the preparation, properties and characteristics of potassium permanganate and potassium dichromate. So you can take full advantage of those videos. But what are these Jones reagent and Collins reagent, right? So to make things simple for you, I've listed them in two columns here. Jones reagent is nothing but potassium dichromate or sodium dichromate in an aqueous solution of H2SO4, which makes it a very strong oxidizing agent. So when we talk about the conversion of alcohols to aldehydes and aldehydes to carboxylic acid, the second step of the reaction requires strong oxidizing agents, although this reaction can also be brought about by acidified potassium dichromate, acidified potassium permanganate as well, because our 1 degree alcohols are very cooperative, right? They undergo oxidation easily, but it is the ketones which are, the 2 degree alcohols which are a little troublesome. And remember, we were talking about using strong oxidizing agents in order to oxidize ketones, or very strong oxidizing agents to convert 3 degree alcohols to ketones. And that is where we talk about reagents like Jones reagent. But what if I want the reaction to stop at the aldehyde? I don't want my 1 degree alcohol to get converted into carboxylic acid. I want the reaction to stop at the aldehydic stage. That means I want a controlled oxidation. And that is where Collins reagent comes into the picture. What is Collins reagent? PCC in CH2Cl2. Oh, this sounds more like French than chemistry. Don't worry. It's pyridinium chlorochromate in methylene. See, you have CH4 is methane. From CH4 you remove a hydrogen, it becomes methyl, and from this if you remove another hydrogen it becomes methylene. That is what we have written over here. Now this is its common name, CH2Cl2. Can you try and give me the IUPAC name of CH2Cl2? Think, how many carbon, saturated or unsaturated? And what about the chlorine? How many chlorine? Prefix or suffix? This PCC is depicted as a pyridinium. So C5H5N, this much is your pyridine, right? And we are talking about pyridinium, that means the ion, right? Chlorochromate, or instead of writing like this, many places and many textbooks you will find it written as CrO3, C5H5N, HCl, right? A combination of pyridine, HCl and chromic oxide. Now this is a weaker oxidizing agent. So with the result, the reaction will stop at the aldehydic stage. That means we are going to carry out controlled oxidation and stop the reaction over here, right? It's a mild oxidizing agent. In all these oxidizing agents, you will see we've got chromium over here. Everywhere the chromium is turning from an oxidation state of 6 positive to 3 positive. 6 positive means the original solution of potassium dichromate would be dark orange red in color. I tried to write it in the color nearest that I could find in the app. But that's so you're probably, if you have better pens, you can write it with the dark orange color. whereas the chromium in +3 oxidation state is green in color. So immediately when this reaction takes place, alcohol turning to aldehyde or carboxylic acid in the presence of acidified potassium dichromate, you will see color changes, right? And what color changes will you see? Yes, of course, orange to green. And when this color change stops, that means the oxidation process is over. What about manganese, right? We are using KMnO4. What are the color changes that happen when we use potassium permanganate? Would you like to know? We have a separate set of videos on potassium permanganate. It will do you good to watch those videos and improve your topic on the transition elements and their compounds. Okay, now this part is for you to do. Try answering these questions. So you have over here ethanol. What will be the products of oxidation? In the case of ethanol, give me the products of mild oxidation as well as strong oxidation. Both. Give me both the options. And also write down what oxidizing agents you can use. Don't try to scroll further because it's a question. It's a very good way for you to practice your skills. That is why pen and paper. You want to improve organic chemistry, you have to write. There is no other option, no matter how many videos you watch. Go ahead with the second one. I've got a secondary alcohol. Look at the functional group. What will be the product of oxidation? Third, a tertiary alcohol. Please complete these reactions and tell me the products which are formed. To know the answers or to check your answers, you can see the slides on Pen and Paper Chemistry Google site, where I will be posting the answers to these equations or the questions that I am going to pose. Now, if you look at this diagram or the chart that I have drawn over here, oxidation of alcohols. I've started with the property, alcohols getting oxidized, right? These are the properties that we are discussing. One is by use of chemicals that we've discussed just now. So what we've done is we've done chemical oxidation, right? The other way that we can oxidize alcohols is by using copper metal as a catalyst at a temperature of around 300 degrees Celsius, wherein what will happen is actually loss of hydrogen takes place. So there are two things. One is hydrogenation. That means when you add hydrogen plus hydrogen, then there will be dehydrogenation. So D means to remove, to take away. So that would be like taking away. Same way, hydration would be addition of water. Wherever you see the word hydration, that means you are getting hydrated. Water is getting added. So what would be dehydration? That means there will be a removal of water, right? So here, back to the topic, we are going to do dehydrogenation. That means a removal of hydrogen from the alcohols using the catalyst copper at a temperature of around 300 degrees Celsius or 573 Kelvin. So what are our observations over here? We see that primary alcohols give us aldehydes containing the same number of carbon atoms. So this is something similar to what we did under the chemical oxidation, right? Next, we see the secondary alcohols. They get converted into ketones containing the same number of carbon atoms. This is also similar to what we've done, right? 2-degree alcohols on chemical oxidation. They are giving us ketones containing the same number of carbon atoms. So I'm confident that you will be able to complete equations based on this. Come to 3-degree alcohols. What happens in their case? Tertiary alcohols, they are finding it difficult to lose hydrogen. So what do? Look at the word that I've written over here. Dehydration happens in their case, and they result in the formation of alkenes. So what do I want you to do? Now again, I have given you 3 compounds, the same 3 compounds, 1, 2 and 3. So first one, ethanol. Second one, propan-2-ol. Third one, 2-methyl propan-2-ol. Complete these reactions and tell me what will be the products formed when they undergo catalytic dehydrogenation. So basically, we are treating it with copper at 573 Kelvin. Remember that in the case of tertiary alcohols, there will be dehydration and not just dehydrogenation. Right? This word is different from this one. Go ahead and after writing the answers, make sure that you check them at Pen and Paper Chemistry on Google Sites. Now that we've covered oxidation and dehydrogenation of alcohols, what do you think should we do next? Okay, we will talk about something very, very interesting. That means the alcohols breaking down at 2 different points. Can we cause the alcohol to break the OH bond, or does the alcohol prefer to break the CO bond? We shall be discussing about these reactions in the next video, so stay connected. And don't forget this flowchart. In case you've not accessed it till now, you can always take a screenshot or you can pause the video to draw this flowchart yourself with the help of colored pens and pencils. It comes in very, very useful to give you a bird's eye view of the topic. Stay happy and enjoy your learning. See you in the next video.